Alright, so here we have a gravity question involving kind of a strange planet here that has a hole drilled through its center. We've been told it's constant density and it's spherical. And we want to figure out the gravitational force on an object that we drop into that hole through the center. Is not as simple as our equation sheet F equals G m1 m2 over r squared expression. Because when we're inside, only part of the mass pulls us down, right? So if our planet looks like that, when we're sitting right here, only the part of the mass that's inside, so like that bit, that's terrible, so only that bit that's kind of circled in blue contributes to the gravitational force. If you want to do it in detail, it's actually a pretty complicated calculus problem, but the idea is basically that the mass that's out here is canceled by the mass that's out there, and only the stuff that's inside sort of net pulls you inward. And that's just kind of an important concept to remember, which is why this problem has been assigned. So, with that in mind, we need to figure out how to represent how much mass is inside when you are a distance r from the center. And if it's constant volume in a sphere, then the mass inside is rho times v, or rho times 4/3 pi r cubed, right? And now the gravitational force, times the mass of the ball times the mass inside over r squared, right? The general gravity. And there's a reason that I put that negative there, and that's because, right, if our radius is in the positive direction, the force is in the negative. And if our radius is in the negative direction, the force is in the positive. So the negative is sort of to flip that direction around. So, substituting in, actually, let's do it this way. Actually, I'm going to have to start that over. So, substitute it in and organizing it nicely rather than poorly. And we notice, oops, lost the negative. We notice that there's an r cubed over an r squared, so we cancel the r squared and the powers of r in the numerator, and we're left with negative 4/3 pi rho g m r. And if we sort of carefully put parentheses in, we notice that this is the constant that we've defined c. So the gravitational force when you're inside a planet is linearly proportional to your radius, right? And that's the constant of proportionality, c, depending on the density of the planet, the mass of the object you're dropping, and the universal gravitation. So that's part A. We've shown that that is the case. Part B. Force is a function of radius. And these indicators that I'm drawing here are sort of multiples of the radius of the planet. So we just calculated that if we're inside, so anywhere from 0 to capital R, the radius of the planet, we have a linear negative relation, right? So that's going to look like that. And we know, in general, right, that's when we're outside the planet, we have the whole mass inside, so we have that same 1 over r squared dependence, so it's going to look kind of like that, right? And that's all it is. The key is to recognize that at the planet's radius, that's where things change. So it's linear in here and inverse square out there. And that's because of the nature of the gravitational force and combined with the r cubed factor from the volume as the volume changes. So part C, now we have to do a little bit more calculus in here. We need to determine the work done by gravity as the ball moves from the surface to the center. So we know the general definition of work. Right? In this case, since we're following along a radius, the gravitational force and the line we're moving on are parallel. So this just is F dr, right? Cosine theta would be 1. And we figured out the force. So in this problem, I'm going to use that constant c that we defined in A, so I don't have to write all those letters. But you can also write c as the 4/3 pi g rho m. That's fine. I'm just going to write it as c. And now I have to figure out our ends of our integral. So we're going from the surface to the center, right? So the order matters. So negative c come out of the integral. The integral of r dr is r squared over 2. And so this is negative c times 0 minus r squared over 2. So we get c r squared over 2. That's the work done by gravity as you fall from the surface to the center. So to determine the speed of the ball when it reaches the center of the planet, well, we know, right, and since we're considering gravity an external force, we're not treating it as a potential energy. So the only energy that we're considering that we're changing to the ball is its kinetic energy. So we start at rest, so this is 1/2 mv final squared equals cr squared over 2, right? That'll cancel the factors of 2. And so we can get that, right? So final velocity from the work energy theorem. Part E, describe. Well, there's a couple different ways you can approach this. I think the simplest and the best way is to recognize that we have a force equals negative constant times a position. So this is the definition of a linear restoring force. And we know that if you have a linear restoring force, simple harmonic motion is the result, right? That's descriptive. You could also say, well, the ball is going to move from the surface to the center, speeding up. When it gets to the center, it'll keep going, but it'll slow down until it reaches the other side right at the surface again. Then it will stop, turn back around, speed up, head to the center in the other direction, and it'll keep going like that forever. It'll never lose energy. That's just a long way of saying simple harmonic motion in the end, though. Right? Once you recognize what this force is, you know what kind of motion you're going to have. You don't need to do a whole lot more to describe it. To calculate is a bit more work, but to describe, you know what it's going to look like. All right, and so finally, part F, an equation that could be used to calculate the time. There are a couple different ways to do this, right? We know that F equals ma. We know the force we have. Right, from differential equations. Well, actually, the acceleration is also going to be negative in this case, so we'll cancel them out. So, so this, or actually, no. So this, that negative should not be there. So this will actually, this differential equation could be solved r of t. And since we know r of t, and if we know the ends of our integral, right, kind of like that, we could solve for the 2 times that happens at. Right, so that would work. The other thing is, if you recognize that this is a simple harmonic oscillator, we know that this is omega squared, and t is 2 pi over omega, right? And so from point P, the surface, to the center is 1/4 of a period. So T P to C equals 1/4 of a period. So that's 1/4 times 2 pi over omega, which is pi over 2 omega, right? And since we know what C is, actually let's write it this way, pi over 2 square root of m over c. Right, so this right here is actually a solution for that time. It's not even an equation that could be used. It is the actual final result. And we didn't actually have to do calculus to do it. We just had to remember from this form of the equation what omega squared is. There's a relationship between the omega and the period, and there's a relationship between the period and the time that we are trying to find. And then if you plug in what C is, you can get the final full result. Okay. So this problem involves a lot of calculus, but if you're sort of careful with recognizing patterns, you can avoid doing a lot of it, which is a really helpful tool to develop.